Thank you for viewing this concept module on map design for the color vision deficient. I want to talk to you about color blindness because this is really a misnomer. We should be calling this color vision impairment or color vision deficiency, and the reason is that most people can see color. It's very, very rare that someone is completely color blind. So color vision deficiency is a more appropriate term. And primarily we're talking about people unable to distinguish between red and green. That's the most common problem, at least in inherited color vision deficiency. And then blues and yellows. Although that's rare inherited, it does become common in about half of the population over the age of 70 or 80. This is what started me on this quest. This was a handout that I was preparing for a student many years ago, and the student told me that he could not see the labels. And using Color Oracle, I'll show you here what that person saw. So the labels were very hard for him to fish out of that background. So that got me interested in this topic, that I wasn't really serving my students well, and then thinking about colors on maps in general. Now, although there is a lot of data on X chromosome, this is mostly statistical data. We know this is an inherited phenomenon, but injury and illness and medication and chemical exposure all can cause color vision deficiencies. We also know that in populations over the age of 70 that there's a yellowing of the lens that can cause a problem in aging populations. Now, in the inherited, well, actually in all color vision deficiencies, there's two categories, I guess you could say, in terms of color vision deficiency. And primarily, where the majority of people fall are males, about over 6% of males and a small percentage of females that have a weak sensitivity to color, and this would be called an anomalous trichromacy. At the extreme, we have what's called dichromacy, where the cone is actually missing. So it's not malfunctioning, they just don't exist. And this accounts for another 2.5% of people that have either red or blue cones that are missing, and it's very rare, red or green cones that are missing, and it's very rare that the blue cones would be missing. Then there's absolutely no data on the actual number of people out there that are suffering from medication, illness, and chemicals. So no data, except on the aging. We do have some studies that show some percentages from the sample population. So why does this matter? Well, as you know, we have an aging population. And universal design and accessibility, we're trying to avoid discrimination. We're trying to comply with regulations. Gardner points out in a really nice thesis from Penn State that if you're doing web design, then you certainly don't want to be designing a sales website where people can't see to purchase products. So they're going to click away. And regardless of who your audience is and what your purpose is, you want to have productivity and customer or user satisfaction. And it's just the right thing to do. So let's look at the trichromacy theory, where we mix colors and red and green give us yellow, and green and blue give us cyan, and red and blue give us magenta. So that's what the average or normal person would see. Now let's take the extreme, protanopia, and this is where we have a missing red cone, and those folks that have this deficiency cannot distinguish as well between red and green. So this would be the extreme. But the good news is, for folks that do suffer from protanopia, some people call these protans, those folks, their red appears dark. So you can use lightness steps to enhance the red. Now the problem is that red and black will look exactly the same, especially if the red is dim. So the lightness matters, and you'll want to avoid red and black for folks that suffer from this. On the left would be normal vision, on the right would be what a person with protanopia would see. And notice that yellow and green are very, very difficult to separate. Now, what about the effects of deuteranopia? And these are folks that are missing the green cones. And they cannot, again, distinguish red and greens, but reds do not appear to be red or dark. So you can't compensate for lightness. Now, while we're here, let's also talk about the population where the majority of people are, which are those that are the deuteranomalous folks that have a weaker sensitivity. These folks can do better discrimination between red and green, and they can differentiate shades a little bit better. Okay, so it's not all or nothing. There's actually quite a continuum of variation on what folks can see. And again, deuteranomalous, they can discriminate a little bit better. Now, in the next example, I'm just going to show you the extreme. So this is deuteranopia, where you are missing green cones. On the left is a normal view. On the right, you can see here the yellow and green are very hard to distinguish and coming closer to the red. And blue and cyan and magenta are somewhat close. In a recent study by Schneck and others in California, where they sampled just under about 900 patients, they looked at aging populations from about 58 to 102 years of age, and they found that it's already known that as people age, there's a yellowing effect, a yellowing of the lenses, or called a tanning of the lenses. And so it has a yellow filtering effect, and what it does is it messes up the blue-yellow vision. And what they found in those 900 people that they sampled was that people that were over 70, 45% of them suffered from this, and half the population of those sampled over the age of 85 suffered from this. And the majority of the problem was difficult distinguishing light blue from purple, and the yellows from green and yellow from yellow-green. So those are the problems for aging populations. And it's something to keep in mind because our population is aging. In Maine, for example, we have one of the oldest populations in the United States. So a number of things to consider. Number one is that color is three-dimensional. In addition to the color itself, or its hue, we also have the lightness. And then we also have its purity or saturation. Also, color has perceptual dimensions. Two colors next to each other may appear differently with different color pairs. For example, I just painted my kitchen and it's a light green, but next to one wall it actually appears blue. Red and green are our most common problem, and most people consider blue to be universally recognizable, but that is not necessarily true in elderly populations. Blue is a problem. So a number of authors have their recommendations. Number one among those is to pick complementary pairs or color sets. Make sure that you do not have ambiguous color combinations. When you're doing mapping, avoid colors for class differentiation. If at all possible, especially if it's point values or line values, you can use other visual variables such as size or shape. And then there's nothing to say that you can't annotate features to show that class differentiation. And then lastly, reduce the number of classes. The fewer classes you have, depending on your interpretation of the data, the fewer classes you have, the easier it is going to be to assign distinct colors and distinct color variation between those classes. Brewer and Clark point out that there are a number of hues of concern. Red, orange, brown, yellow, beige, and green can be confusing. They also point out that magenta, gray, and cyan can be indistinguishable. The other thing that they point out is that red and black combination should be avoided. And where does color matter? It matters where you are trying to put meaning attached to that color, right? Darker value, darker color, higher value kind of meaning. But one of the things you can do is, if you have a color that you can use and vary the lightness steps, you can use that to differentiate the range. These are a number of the color pairs for web and map use that are recommended by Brewer and Clark. I'm going to skip over this, but you can always come back and reference, and also reference their articles. Now, specifically when it comes to mapping, let's talk about point and line features. And one of the things that we do is that we know that saturation or purity of color only helps slightly when it comes to the red-green impairment, right? Jenny and Kelso mentioned that it's better to shift from green, away from green, to blue. And your best solution is, similar to other authors, vary the shape and combine that with variable colors, variable hue and saturations, and annotate. So this is a number of 3 different authors that mention the annotation and using different visual variables. So as they point out, the best maps are the easiest to decode. And of course, we know the universal constants, right? What is your purpose and who is your audience? Now, what do you do for raster or areas or polygons? Again, we can vary the lightness, especially on the red, orange, yellow end of the spectrum. We can omit yellow, green to avoid the green confusion. A lot of people are avoiding green altogether. So use a red, orange, yellow, light blue, dark blue progression. And what you can do is, if you do have a data transition, make sure that your yellow to blue transition is at a pivot point in the data. So that's pretty clever. So here is a digital elevation model, and you can see here that I'm using a normal color ramp from an Esri product. And what I've done is, now I'm showing you what someone suffering from deuteranopia will see. So you can see there's a little bit of a loss of detail there. It's actually better than I anticipated. And then here's a modified ramp that goes brown, kind of yellowish white, to light blue through purple. And there is a loss of information in the upper right in both images, not between the images, but I think initially. So Jenny and Kelso use more of the red, orange, and yellow to a light blue through purple, and they do a better job of this than I did. So check out the Jenny and Kelso article. Dr. Brewer at Penn State says, be careful when you're choosing colors using values, because the tools themselves do not include the perception, right? They're not perceptually scaled. So you really need to do this by eye. She stresses that. But she also provides us a tool that will allow us values that we can plug in there. Brewer has also identified what she calls colorblind confusion zones. Her recommendation is, if you skip a zone, if you choose a color from not adjacent zones but every other zone, you will avoid confusion for those people who are colorblind. I do not have copyright to that image, so I will encourage you to find that in her Esri text called Better Map Design, and also go to her website at Penn State, and at the URL below, page down till you see the figure 4.5, which is right out of that book, and you'll see the zones in question. Number of resources to recommend to you. Top on the list, if you're making maps, is the Color Brewer, where you can set the number of classes that you're using, and she will give you color recommendations that are clearly distinguishable. And there's even a little checkbox for the colorblind color recommendations. The Color Oracle is another tool you'll definitely want to download onto your computer and run it, which does show you the extremes of what a person that's colorblind would see. And then these other references or resources. I thank you for taking the time to listen to this iGETT module. I hope you found this useful. My references are listed here. I'll let you page through yourself. These are followed by questions and answers. Again, feel free to page through by yourself, back and forth as you need to, and thank you for your time.